Hey, honors physics, we're going to take a look at Coulomb's law. We started the other day, but we're going to now look at a couple of kind of other anomalies, different versions of this formula. So let's get right into it. So let's take a look at these hot air balloons. We're on the bottom of page 24. And these hot air balloons have to really watch out for each other during landing and takeoff, especially when there's like balloon festivals, because the surface of these balloons becomes highly charged as they're moving through the air and the hot gases that are kind of filling them. It tends to make balloons charged, and so they will tend to actually attract each other or sometimes even repel. But if they're close together in a field, there's going to be some interactions. And what we have here is we have a known charge. Each balloon has a charge. Q1 and Q2 are both 3.0 times 10 to the negative fifth coulombs. And if you keep reading through the problem, the question is, what is their distance of separation? We don't know that. But we do know that the force between them is small, but it might be large enough to cause some chaos, to have these balloons collide. I'm not sure that's going to cause them to fall over, but we still don't want them bumping into each other, right? They're too large and they've got hot gases and there's passengers involved. So what we're going to do is let's zoom in and we're going to set up Coulomb's law formula. And I bet the vast majority of us at this point in the year can handle rearranging this formula or just plugging in and solving for a different unknown, right? The unknown does not always have to be on the left side or all by itself. So let's plug in 8.1 times 10 to the negative second newtons. K is 9 times 10 to the ninth. The Q's are known, 3.0 times 10 to the negative fifth coulombs. And don't forget to square, right? Each of the balloons takes on the same charge. And the distance of separation is the unknown. So it really depends on your maybe calculator skills or your confidence with math. But essentially, you need to isolate that distance. And I'm going to hit pause and find the answer. Did you take the chance to do that? I got that the distance squared between these two balloons is 100, and so that's the distance squared. So the distance is actually 10 meters apart. So I don't think this causes too much challenge. If you need help or support with actually doing the rearranging, multiplying both sides by d squared, uh, dividing by 8.1 times 10 to the negative second, and don't forget, of course, there's a square root. So that's a pretty basic Coulomb's law, right? But now we have a different unknown. You're going to do a few in class. We're going to actually check in on this one, and each of them has a different unknown. Here, the unknown is, let's see, each charge, let's say barely touching. If the force is this, how far apart? This is another distance is unknown. In the bottom of 25, with these packing peanuts, styrofoam packing peanuts, the charge will be the unknown. So when you set up your formula, and I'm going to model it, but I'm not going to complete it for you. You would plug in your force, you would plug in your K, you'd plug in the distance. But how would we deal with these two unknowns? Well, when you are pouring out things, it could be Cheerios, grains of salt, sand, or even these styrofoam packing peanuts. What happens is that when they fall out of their container, right, they come falling out, they always acquire the same charge and they will spread out. So the charge of every single one of these, when you're dealing with what's called like bulk flow of materials, and you might say, well, how did they even become charged? Well, as they go pouring out of their container, that's friction. And so the answer to how do we solve for two unknowns is we don't. We're just going to call it Q squared, and you'll plug in your K, your F, and your distance squared. That was supposed to be a check mark. So you really only have one charge, and that will be the charge of both of those objects. Okay. There's a couple more. What will be the force of repulsion? That's a force is the unknown. And then what is the magnitude of the charge? Another Q unknown. So it's good to do like one or two of every single type. And that's how you use Coulomb's law for like some application. Okay. Now, there's a homework assignment due tomorrow, which is things that you can complete on your own. They might have to do with rubber balloons rubbing, and we're trying to find the electric force. Let's see, here we're trying to find the charge. Here we're trying to find the distance. So I'm pretty sure it's like one of each, and you're doing one, two, three on page and one, two, three on the next page. The third one is a really interesting application if you're an environmental scientist or you care about clean air, because what it actually describes is something called a scrubber. A scrubber is found in a power plant that burns fossil fuels. And I bet some of you know that the pollution that comes out of the top of a smokestack, the waste, can be things like nitrogen compounds or even sulfur compounds, and it leads to acid rain, and that's not good. Nitrites and sulfites, when they mix with water, form sulfuric acid and nitric acid. And those have to be reduced through other chemical means. But what about the actual particulates? There's actually a lot of ash that comes out, and ash is very staticky, it's charged. And to reduce the incidences of asthma, they have installed electrical scrubbers. And it's a wire mesh. It's very durable, can handle high temperatures. And what it does is it creates positive and negative charges, and the particles will start sticking to them. And all of a sudden, they stick, they fall down, they're captured, and it's better than putting it into the atmosphere. Arguably, let's just start reducing fossil fuels and make our electrical system, our energy grid more green. But there will be a place for fossil fuels for the foreseeable future. Okay, new idea, new lesson. Okay, Coulomb's law. Did you notice that everything we've done so far is Coulomb's law between two particles? What if we have a three charge system? And each of those objects has a charge. And if you look really closely, right, on them, we've got a -2, a positive, and a +1. These are assumed to be one apiece. And what you might find yourself needing to do is to find the net charge on a single, right, member of that team, of that trio. There we go. And what you have to do is you have to really make sure you pay attention to what charge is in question. So on number one, we want to find the total amount of force due to the electrical force on Q2. And what we're about to do is something called the principle of superposition or the law of superposition. And what that says is that before we even get into the math, get into the weeds, we're going to have to realize that we're going to have to find the sum of all forces or components. Oh, we know how to add vectors. So let's first take a look at. Now, I wish I could kind of cover something and hide it for you, but let's pretend Q3 doesn't exist. Let's ask the question, what does Q1 and Q2 do to each other? Well, they're both positive, so they repel. And what we're going to do, and you're like, oh, that's easy. They just repel, they're outward forces. Let's label that force with what force is it? So this is force 1, 2. One is pushing two to the right. And then over here, we have force 2, 1. And it really helps to use color. Or if you don't have color, you can use like a dash line. I'm going to use color. So we just examined what 1 and 2 do to each other, but we ignored 3. Now what I want you to do is to ignore 1 and ask yourself, what does 2 do to 3? And those are also both positive, so they also repel. And let's label this one. This is force 3, 2, and this is force 2, 3. Remember those forces, the two red forces, right here. Let's grab my laser pointer here and here. Those are the same magnitude, but they're in opposite direction, just like the two blue forces are equal and opposite. So what we're going to do is now we're going to get rid of all this clutter, and we're going to draw the free body diagram for just charge 2. So what do we have? We've got one force to the right, and that's force 1, 2. And then we're going to do the red one and label that force 3, 2. And what you probably are foreseeing is that we're going to have to just calculate each of these individual forces. So let's do the electric force between Q3 and Q2 divided by the distance between them. And then let's do a second calculation of Q1 and Q2 separated by the distance between those two. So we've got 9 times 10 to the ninth times 3. And where do you get the charges? Okay, they're right here in the original problem. But what do you do with the micro? You turn it into scientific notation because we need actual coulombs. So 7 times 10 to the negative sixth is the charge on 3, and the charge on 2 is 12 times 10 to the negative sixth coulombs. And I bet some of you are like, that's not proper scientific notation. Your calculator can handle it, and it will fix that. Okay, the distance between 2 and 3 is 0.02 meters. Don't forget to square that. So take a minute, calculate that force, or maybe hit pause and calculate all of these. Did you get your answers? So I got the first force to be 1,890 newtons, and this one I got to be 864 newtons. Okay, why are they so strong? Well, because they are very close together. And that's what happens with an inverse square law when you're dealing with incredibly short distances, 2 centimeters, 5 centimeters. Now, here's the hard part or the challenge. So look back at your free body diagram. When you calculated or drew in this one, force 3, 2, you drew it to the left because 3 was repelled by, 3 repelled 2. So to the left, right? It's up here. So what we need to do is to remember that that therefore has to become a negative vector, and the 864 has to be a positive. So the result, when we finally add them, right, one's to the left and one's to the right, is 1890 negative plus 864, or a net force of 1026 newtons, but it comes out negative, and that's our net force. So the middle charge would be pushed with a considerable force to the left. Okay, go ahead and try the second one, and I'll put the answers up in just a minute. Let's check in on how you did. When you plugged in your Ks, your Qs, and your distance, did you carefully get 64.2 newtons, but to the left? And when you plugged in your K, your Q2, your Q3, and your distance, did you get a positive 157? And now all we have to do to find the combined force or the net force is we just combine those. So negative 64.2 plus 157. 0.4, nope, 0.5, is you get a net force of 93.3 newtons, and it came out positive. So the net force, so Q3 would get pushed harder to the right. And in many ways, that kind of makes sense because Q2 has a smaller charge, but it's so much closer than the pulling force of this larger charge that's almost twice as far away. So closer charges have bigger influences. So the 157 dominates moderately over the 64, and we get a net result of 93. Here's where it gets a bit more fun. This is really fun. Okay, what if we have an equilibrium? What if the middle charge is trapped? Well, what does it mean to be at an equilibrium? It means the total force on the middle one is 0. Well, how could that be? The only way that that can happen is if there's a tug of war, there's two forces, and we've got force 3 comma 2, 3 pulling on 2, is the same magnitude of 1 pulling on 2. And that does make sense, a positive and a negative attract, and then a positive over here and a negative attract. So it is a tug of war with a stalemate or an equality. Now you might say, but one's negative and one's positive. Absolutely true. But when you calculate Coulomb's law, do you remember that it's an absolute value? You're actually calculating the magnitude of the force. So therefore, what we're going to do is we're going to say force 1, 2 is equal to force 3, 2. And you can put them in absolute value, but basically, if we're going to use Coulomb's law, then we don't have to worry about direction. And let's see what happens. Well, the first thing we can do is we can plug in an equation for each one of them. Let me make this just a little bit more discernible. K times Q1 times Q2 over the distance between 1 and 2. Now, this is where I maybe rushed in. The distance between 1 and 2 is unknown. We're trying to figure out where to place the middle charge so that it is set up for an equilibrium. Like you can shift it and place it. So we don't know that value, but it's an x in the picture instead of a d. And that's our unknown. We're going to be solving for x. On the other side, what's the force between 3 and 2? Well, that's K, Q3, Q2. The order doesn't matter. And what's the distance over here? Oh, I bet a lot of you have done word problems like this in a math class where the missing distance is the total minus the x that we don't know. That way we have an unknown in terms of another. And this is where some people get a little intimidated. They think to themselves, that's a beast. I have to plug in all of that. I have to do a quadratic. I have to square that polynomial. I bet you're going to see some things cancel out. K, K, Q2, Q2. Now we do have to plug in Q1 and Q3, right? No, let's deal with the denominator. The denominators are squared in both of these. And I'm not afraid of expanding this polynomial. Shouldn't be that hard. Algebra 1 skill, but I'm going to suggest that you do this instead. And I don't know if we have any math theorists among us who notice that when you square root a polynomial, you are actually getting rid of a root. But we're going to be throwing out a root, right? Because if it's a polynomial to the second power, there are two roots. But when you square root it, you get rid of one of the roots. And the root we're getting rid of is not a valid root. If you did it the expanded way, you'd see that you get an answer that doesn't make sense. So now what do we get? We get the square root of q1 over x, right? The squares are gone. And we get the square root, oops, let's do that in blue, of q3 over 0.05 minus x. The square is gone. Now I guess we eventually have to plug in, but that looks much more manageable. So what's the square root of q1? 9 times 10 to the negative sixth, square root, and you get 0.003 over x. Square root of 3, what's the square root of 3 times 10 to the negative 6? And you get 0 point, hey, come on, pen, 0.00173 if you want to keep 3 sig figs, divided by 0.05 minus x. And from here on out, we just need to simplify this expression. We're going to cross multiply 0.003 times 0.05 minus x equals 0.00173 times x. All I did was cross multiply. Let's distribute 0.003 times 0.05, 0.00015 minus 0.003x equals 0.00173x. Combine like terms, 0.00173 plus 0.003. And I got on this side 0.00473x equals 0.001, oops, don't drop a zero, 15. And now we just have to find x. And let's hope that at the end of the day, the x is a number that's smaller than 0.05. It has to fit in the middle of that. So what's the position? So 0.00473 divided by, oh, excuse me, the other way around. Nice work, Hausman. 0.00015 divided by 0.00473. And you get 0.031. And that is exactly what we sort of hope, that it is smaller than the original distance, 0.05, and that's meters.